show that this fraction reduces to a natural number. Let's call this, so we don't have to write it down every time, let's just call this numerator NUM. Okay, the numerator is a 16-digit number just comprised of ones, and we're trying to show that this numerator is congruent to 0 mod 17. Let's write that down. Probably get away without writing this down, but we can write down num. And again, you could have stated the problem like this. Okay, num is congruent to 0 mod 17. Now, formally, you can think of that as just saying num minus 0 is divisible by 17. Okay, so again, whatever you prefer, it's just a matter of style how you want to write this, but both of these statements are equivalent. Okay, now, also notice that numerator has a decimal expansion. Okay, NUM is equal to all of these powers of 10. Okay, so the numerator, this numerator is equal to, this is just the decimal expansion right here. Now, another thing to notice right here is that a very, very super useful result right here is to use this result called Fermat's little theorem, and it's of the general form if this is P being a prime, okay, then 10 to the P minus 1 is always congruent to 1. 10 to the P minus 1 is always congruent to 1. And the proof's kind of interesting. I just went through it the other day. It's kind of nice. But anyway, we'll just use it as a fact. We know that 10 raised to the 16th power minus 1 is divisible by 17, okay? And so at this point, we know this restatement, 10 to the 16th minus 1, we know that this part is divisible by 17. Let me just write that down up here. So another way to state Fermat's little theorem is just, for this special case, is to say that 17 divides 10 to the 16 minus 1. And we're almost done with this thing already. Fermat's theorem is powerful. Minus 1. Or it's Fermat's little theorem guarantees that 17 is a divisor of 10 to the 16th minus 1. Another way of saying that is 10 to the 16th minus 1 is equal to some multiple of 17. Okay? So you see what happens right here is we get all of these terms right here just become 1, right? And so what we get is this is equal to 9 times our numerator. Okay, I'm glad I gave that a name, aren't y'all? Okay. So it's equal to 9 times the numerator, which is the object we're, remember we call that the numerator. All right, so we know that 17 must divide 9 times the object we're interested in. But you know there's a famous result that if, let me write this a little more. There we go. So we know 17 divides the product of 9 and the numerator, but there's a result that says if you have a prime dividing a pair of integers, it has to divide one or the other, right? Okay, so this implies, see, clearly 17 is not a factor of 9, so that implies that 17 divides the numerator. Okay, 17 divides the numerator. And another way of saying that is the numerator is a multiple of 17. Okay, so let's go back up. So the numerator is a multiple of 17. And so right here, if the numerator is equal to some multiple, we'll just write it 17m, right? Okay, then it does resolve the 17. This 17 will cancel with this 17 right here, and we'll get a member of the natural numbers. Remember, the natural numbers are just the numbers the positive integers 1, 2, 3. Oops, it's supposed to be a 2. 1, 2, 3 all the way out. Okay. You know, sorry, as usual, I couldn't keep that on everything on the screen, but all of this writing this expression in this factored form. Now, maybe a word I should mention one thing about how could this expansion actually just equal to this. This is example what they call telescoping. Notice that this right here would give you minus 10 to the 15th, okay? But then these guys right here, let me get that, okay? This would give you 10 to the 15th, but 10 combined, excuse me, I'm sorry. Yeah, we got it fine. Okay, this gives you 10 to the 15th, right? Ten to the 15th. But then the piece right here would give you minus 10 to the 15th. You see that, folks? So these terms cancel out. A lot of the terms cancel out power. Everything cancels out except for 10 times 10 to the 15th, which is 10 to the 16th. And then this minus 1 times this minus 1 right here. Now, it'll get too messy to show you that, but I think you guys could see that. It's an example of a telescoping sequence, I guess, or factorization, whatever you want to call it. But in any event, the other primary result is that this whole thing is equal to 9 times the numerator. But we know from Oswald's theorem that means that 17 must divide this product. Okay, but if 17 divides the product of two integers, it has to divide one or the other. That's the same thing is not true of composite numbers, but it is true of prime numbers. Okay, so we are done. We showed the numerator was a multiple of 17, hence the entire fraction was a natural number.